Okay, let's take a look at Galilean relativity and look at a classic problem that we use to illustrate Galilean relativity that we might work with for motion in 2 dimensions. So one way we can look at this, one sort of problem we might play with, is looking at how a boat or a swimmer may move relative to a river and its current, and compare that to their motion relative to the shore. So in this example, I say that our water, the river current, is moving downstream at 5 meters per second. And I'm saying that downstream is 0 degrees from downstream. Whereas I'm going to say, all right, let's say that we have a boat that is traveling to cross the river, and it's going at 7 meters per second, and it's aimed directly across the river, so that relative to the water, it's moving at a 90-degree angle relative to the current. And I want to know, well, what's that velocity relative to the shore? So we're trying to find a resultant vector, and that resultant vector is the velocity of the boat relative to the shore. And so we take a look at this situation, and we know from Galilean relativity that the velocity of the boat relative to the shore is equal to the velocity of the boat relative to the water plus the velocity of the water relative to the shore. We're doing vector addition. And with vectors, they're adding them up in that way. Now in this case, the vectors are oriented perpendicular to each other. They add together to form a right triangle. I've selected a special case version here. But to illustrate, I'll set things up in a more general fashion. And so what we want to do is say I'm going to pick a coordinate system where the current is flowing in the x direction and directly across the shore is the y. And in that case, we want v boat water in the x direction plus v water shore in the x direction to yield v boat shore in the x direction. And so that's v boat water, that's 7 cosine 90 degrees, which is 0 for its downriver component of motion. And then that's 5 cosine 90 degrees, which is 5. So as stated, it's 5 meters per second for the x component of our motion, and the y components are related through the sine of their angles. And so, as illustrated, the y component is 7 meters per second. So again, we could have seen that by inspection with the particular angles given for this problem, but we've sort of formally illustrated how we could do that if the angles were a little different. So now we add the vectors together like we would for any situation. And let me give us some more space here. We essentially need to find the length of that hypotenuse to find the speed, the magnitude of our velocity. The velocity of b with respect to s gets to be the square root of the velocity of b with respect to s in the x direction squared plus b with respect to s in the y direction squared. So it's the square root of 5 squared plus 7 squared. So square root of 74. More than 8 and less than 9. A little less than 9 for that. So what is it exactly? 8.6 meters per second. That's insufficient. We need to know direction. This is a vector quantity. And so we want to know what angle this is. Now, we could look for the angle that's interior to this triangle here. I've been measuring my angles away from the shore. So I'm interested in this angle here, in this case. And to do that, that's the same as this angle there. So it's still the inverse tangent of the y component divided by the x component. The way that we've laid this out, so that's the inverse tan of 7/5, and so inverse tangent of 1.4, and that's about 54 degrees. So then our final answer for this, write it out, is that the velocity of the boat relative to the shore is 8.6 meters per second at 54 degrees from downstream. Or from downstream towards the opposite shore, or something to that effect. So, there we go.